Hello, everyone, to the 10th and last lecture of DeCifrisTrends in cryptographic protocols. In this lecture, we will see some advanced cryptography that is used in the context of e-voting. I am Riccardo Longo. I am a researcher in applied cryptography in the Center for Cybersecurity of the Fondazione Bruno Kessler. Aleph is the name of the research unit that studies applied cryptography. So let's come to today's topic. What is electronic voting? Electronic voting is a very broad term that just means to exploit some digital technology to enhance somehow the voting process. The main goals of electronic voting are to increase accessibility and encourage participation. So take away some barriers that are from voters to actually participate in elections. And the other main goal is to improve the tallying process, from speed to accuracy, and to add some verifiability that in many cases in the paper-based elections is not quite there. So these are the main goals of electronic voting. What do we want from e-voting protocol? We want to have some security assumptions, some security properties, that these are quite general for any kind of election, but we want to transpose them in the electronic solution. So first of all, we want vote privacy. That is, no one should get to know how someone else has voted. So preserve the privacy of votes. Then we have fairness. We do not want that someone gets knowledge, even partial knowledge, of results before the end of the voting period. This is to preserve the fairness of the voting process and avoid that some leaked information could influence how some voters behave. So we do not want that partial results came out before the end of the voting protocol. So we want to have a voting period, then we stop voting, and then we start tallying, and at the end we have the results official for everyone. Of course, the other very important property is eligibility. We want that only eligible voters should be able to cast a vote that will be then counted. And most important, we want that no one should be able to vote more than once. So we want to enforce the rule, one head, one vote. That is a classic staple of democracy. Then we have the added properties that we would very like to have, but they are not so obvious to get. First, we have verifiability. That is, it should be possible to check that the whole process has been run correctly. So we want to be able to verify afterwards that everything has run smoothly and that there has not been any kind of problem and no one tried to or managed to interfere with the voting process. And finally, the most subtle of all properties, that is coercion resistance. That is, voters should be able to vote freely, to express freely their real intention and not worry about coercers that instructs them to vote in a certain way. And also, we do not want voters to be able to sell their own vote to others. So we want to be able to resist coercion from an attacker and also a willing voter that wants to sell their own voting ability, to avoid that someone gets to effectively vote more than once by proxy to these willing voters that want to sell their vote. So this is a series of lectures about cryptography. So no one will be surprised that we can use cryptography to obtain some of these properties, or at least cryptography can help a lot in secure an electronic voting process. The approach that we will have in this lecture is that we will start from the naive approach. So we have a basic problem. Let's propose an immediate solution. Let's see what are the problems with the naive solution and trying to refine with more advanced techniques. We will mention a lot of primitives and protocols, so we'll not have time to see how they work. So we stay on a high level, but we will you will have an idea on how we can use cryptography to solve some of the problems that we encounter in electronic voting. So, disclaimer, electronic voting is a very hard problem. There are a lot of moving parts, there are a lot of intertwined things that do not want to work well together. And in particular, when we, as we will do, focus on remote or internet voting, that is, we have not the security given by some voting booth, that someone that assure a safe place where to vote, but we suppose that voters vote from home. Then there are a lot of problems that arise, and in particular, we will not be able to see a complete protocol or a whole solution. There are some proposals out there, but no current proposal actually satisfies every desiderata that we have in a voting protocol. Every solution has to make some compromise. So the focus of this lecture will not be how we can solve electronic voting, but because we cannot solve electronic voting, but we will see how we can use cryptography to tackle some problems and which are the limitations of cryptography. So I have made my disclaimer, so let's dive in the topic. First of all, we have the problem of privacy. So how do we tackle the vote of privacy? Very simple. We want to hide the vote content, so we encrypt it. The basic solution that we can think of is asymmetric encryption, because we can distribute just one public key for everyone. The voters use all the same public key to encrypt their vote, and then the authority that will perform the tallying then can afterwards decrypt the votes and compute the results. Of course, there are some obvious problems. For example, the authority can see everyone's vote contents. So we have to trust the authority not to break privacy. And this is an assumption that we don't really want to make. Other problem, if you want to have some verifiability, then in the verification process, we should be able to see that the tally is correct. And how can we do that? We have to see the plaintext. So we will have to reveal the content of the votes. And so we do not have really achieved privacy. How can we refine this solution? For example, we can start by introducing threshold cryptography. In threshold cryptography, we distribute trust among multiple parties. In this way, there is not a single entity that can decrypt the votes and subvert privacy or fairness. For example, in the previous case, the authority could decrypt the votes before the end of the voting period and reveal some information on how the election is going, and thus break fairness. With threshold cryptography, we can avoid this problem if we trust that at least some of the authorities are honest. So what are the techniques that we use? They are distributed key generation, so that no single party has control of the private key, and then threshold decryption. So we have that T out of n authorities have to collaborate to decrypt. In this way, we can mitigate the potential problems of one or few rogue authorities that want to break our security assumption. Of course, we have not solved the problem of the clash between privacy and verification, because for verifiability, we still have to decrypt and publish the results. But we have at least made a step toward something more practical. How to solve the problem of privacy? We could aggregate the votes before decryption. And here we have partially homomorphic encryption that comes to the rescue. Basically, the idea is that we want to see the tallying as a sum. You can say that when you are counting the votes, you simply sum 1 or 0 for each ballot to the total of votes gained by each candidate. So it's not a far-fetched idea. Then, if we have the tally that is basically a sum, we can use an additively homomorphic encryption scheme to perform the tally directly on the ciphertext. In this way, we do not have to decrypt the ciphertext and then count the votes. We can sum the votes with directly using the ciphertext and then decrypt only the result. In this way, we do not have to decrypt every single vote to obtain the results, and we do not have to publish the decryption to have some sort of verifiability. The problem is, how can we be sure that each vote counts as one? If anyone can encrypt whatever, instead of encrypted one vote, one could encrypt 1,000 votes and magically have the power of voting 1,000 times in one go. Before addressing the problem, we can see our first example, that is an additively homomorphic encryption scheme. Here we can see the exponential El-Gamal encryption scheme. It is based on the discrete logarithm problem. And we have a cyclic group G with prime order P. And we have 3 generators, G0, G1, G2. We have the private key as 2 integers modulo P. And then the public key is the multiplication of the 2 generators G1 and G2 elevated respectively to X1 and X2. So we have this public key and the private key. How can we encrypt? The encryption of the message M, that is a number, in practice it will be a small number. So we can see that it will always be some integer modulo P. We have some randomness R, again in ZP. It's important that it's generated uniformly at random. And then encryption, the ciphertext is a triple, alpha, beta, and gamma. That is G1 to this randomness R, G2 elevated to the same randomness R, the public key elevated to the same randomness R, multiplied by the generator G0 elevated to M. To decrypt, we can compute G0 elevated to M, basically elevating alpha and beta to X1 and X2 respectively, that are part of the private key, and then dividing the third element of the ciphertext by this multiplication. But then we have to brute force the discrete logarithm of this value. Note that if we have small values as M, this brute forcing is easy. And in our case, we will see in a few slides that we actually have very small numbers. So this it's not a problem not to compute this forced discrete logarithm. And we can compute it very efficiently with just a pre-computed table. So it will be just a matter of lookup in a table and translate the G0 to M to the value of M. You can easily see that this scheme is homomorphic in the sense of addition. and to have the homomorphic addition of ciphertext, we actually perform pointwise multiplication. So we multiply each member of the triple with the corresponding member of the other ciphertext. And we can see that this multiplication, we obtain the encryption of m plus m first with the randomness that is the sum of the original randomness, and the public key stays the same. So we have our additively homomorphic encryption scheme. How can we use this? We can encode our ballot in this way. Suppose there are n candidates, C1 to Cn, and suppose that each voter can express up to pre-preferences among these candidates. So the vote will be a tuple when each element is just either 0 or 1. And this will express whether the voter wants to vote for CI or not. So if he wants to vote for VI, he will put 1 at the corresponding place. If the voter does not want to vote for CI, then VI will be 0. So to perform the tally on this plain text encoding of the votes, you simply have to sum element by element all the preferences expresses. And you obtain the number of preferences obtained by each candidate, because it will be either 1 or 0. To validate a tuple and decide if it's a valid encoding of a valid vote or not, we have to check two things. First of all, we have to check that each one of the VI is either 0 or 1. That is to avoid that someone makes malicious things like voting multiple times by putting a 2 or 3 or whatever, or even that someone tries to subtract votes from someone else by putting -1 or -2 and so on. So first of all, we have to check that we actually have either a 0 or a 1 in each position. Then we want to check that the voter does not express more than p preferences. This is easy. Once we know that the VI are either 0 or 1, we can just sum them and check that the result is between 0 and p. So if we are able to perform these two checks, then we have that the vote is valid. To encrypt the ballot, we simply encrypt each of the VIs. As anticipated, we encrypt only small numbers. 0 and 1 are very small numbers. And also in when tallying, if we sum all the preferences, also if we have a total of a few millions of votes for some candidate, a few millions is still a relatively small number with respect to the discrete logarithm problem, so we can easily decrypt it. Maybe we'll have a quite large precomputed table, but it's doable, perfectly doable. So we have our possible solution for this encryption scheme. As you may have spotted, we have still to validate that the vote is indeed correct. And this is a problem for verifiability. And to solve this problem, we have zero-knowledge proof that come to the rescue. Basically, what we want to do is to prove that we have followed the protocol, but we have a lot of private data that are involved in the protocol. For example, we do not want to reveal the actual content of the vote. We just want to prove that we have cast a valid vote. So that all the conditions that we saw before are respected. Fortunately, zero-knowledge proof do exactly that. That is, they allow us to prove some statement about some secret data, without revealing the data itself. What is non-interactive zero-knowledge proofs? It's a zero-knowledge proof that is rendered non-interactive via a transformation that usually is the Fiat-Shamir transformation. That is basically means hash the public values and commitment to compute the challenge. So we have some assurance that we cannot cheat and choose the challenge before computing the commitments. We have that any Sigma protocol any zero-knowledge proof that is modeled as a Sigma protocol, if it has special soundness, we can make it a non-interactive zero-knowledge proof with all the good properties that we want from a zero-knowledge proof. In this way, we have a non-interactive thing, so we can attach this string, basically, it's a byte string, to any computation step to prove that it has been done correctly. And then anyone can check the NISQ and verify that indeed everything runs smoothly. What are the problems? Basically, all is good, but not every cryptographic protocol is zero-knowledge friendly. There are a lot of cryptographic protocols that are not very nice to zero-knowledge proof. You can prove that it has been done correctly, but it's very, very expensive, or the proof is huge. So we have to be very careful when choosing the primitives. Fortunately, for the IRGAMAL crypto system, we have a series of zero-knowledge proofs that are quite efficient, and we can use them to prove basically anything we need. The base is Schnorr's proof of knowledge of a discrete logarithm. That is, we have two elements of the group G, G and H, and we want to prove the knowledge of an integer row in ZP such that H is equal to G elevated to the row. That is, rho is the discrete logarithm of H with base G. Starting with this very basic proof that is very easy, you can look it up and it's very nice. We have a variant by Okamoto that allows to prove the knowledge of a plaintext given an IRGAMAL ciphertext. And then from this other proof, we can derive a proof of plaintext equality. That is, we have a plaintext ciphertext that is the triple A, alpha, beta, and gamma, and we want to prove the knowledge of the randomness that we use to compute this triple as the ciphertext, the encryption of M for the public key H. That is, the public key is known, the message, the plaintext is known, the encryption, the ciphertext is known. We want to prove that indeed that ciphertext is the encryption of that message. Of course, this proof is not very useful to hide the message because we need the message, but from this basic proof, we can use to prove that we have encrypted one of the possible values of the message. That is, we can prove that the ciphertext encrypts either 0 or 1 using a very nice technique by Kramer, Damgard, and Shoemakers that allows to prove in general the disjunction of statements. The basic idea of this of their trick is that normally you have a challenge for the zero-knowledge proof that is fixed. You cannot see it in advance, and if it's indeed unpredictable, then you have the soundness of the protocol. But if you can predict the challenge, then you can cheat and produce a transcript of the zero-knowledge proof that is basically valid, but it actually doesn't can be done for anything, any statement, even if it's not true. because we cheated by knowing in advance the challenge. So we fix not the challenge, but the sum of the challenges of the subproofs. This means that we have free choice on all of the sub-challenges but one, because if we choose whatever we want for example, 2 out of 3 challenges, then the last challenge has to be the difference between the fixed sum and the sum of the free choices that we made. So we can cheat in all but one of the subproofs. But this is exactly the disjunction of the statement. That is, at least one of the statement is true, but you can cheat in all the other ones. So if you use this trick, we can easily prove that we have encrypted either 0 or 1 without revealing what we actually encrypted. And so we can prove that our ciphertext has been computed correctly. Of course, we can extend with more values. The proof just becomes a little bit bigger, but the basic principle is the same. Let's go on. Another possibility of preserving the privacy of the votes is to shuffle the ballots before tallying. That is, instead of directly decrypting the ballots in how they are cast, we first shuffle them and then decrypt. So even if we reveal afterwards the content of the votes, we are protected against a lot of possible attacks. Not all of them, but we have some protection. So we have to verifiable shuffle and re-encrypt the ciphertext. Why re-encrypt? Because we have to hide the connection between the ciphertext, the original list and the shuffle list. Note that if we have an additively homomorphic ciphertext, the re-encryption is easily done just by adding the encryption of 0, because we do not actually change the ciphertext, but we modify it so that the two ciphertexts seem unrelated. Of course, we need an uninteractive zero-knowledge proof that the new list of ciphertext is just our encryption of the original list modulo a permutation. Unfortunately, I cannot show you an example of this kind of primitive because they are quite complicated. The basic idea of one of the most efficient ones is that if you permute the roots of a polynomial, you obtain the same polynomial. And from this basic idea with a lot of intermediate steps, they can prove that indeed the new encryptions are just a permutation and re-encryption of the old ones. To return in the setting of multiple authorities and the distribution of trust, if multiple authorities each make a mix, an encryption, and prove their work, then no one can track the ballots unless they collude. So we can effectively mix all the ballots, and no authority will be able to single-handedly track and link one of the original ballots to the final list. The problem is that this protocol is quite expensive, so there's some theoretical work to do on this aspect. And there we have some problems with eligibility checks. In particular, to prevent double voting, we have to be very careful how we mix and when we mix in order to be able to perform all the checks that we want to do. But it's a very, very nice primitive that is very useful in electronic voting. Then let's tackle a bit of the eligibility. the first idea will be simply digitally sign the ballot. If you are an eligible voter, your public key will be included in a list of eligible voters. And so anyone can check that the ballots are signed and therefore made by eligible voters. The problem is quite obvious, that anyone can see who votes and track their ballot. And so we have the first clash with coercion resistance. Here, the very basic attack is that if a coercer tells you you cannot vote, if you use digital signatures to sign your vote, the coercer will immediately see if you try to vote. And this is a problem. So we can go a little bit more complicated and use linkable group signatures. The idea is don't reveal who signed, but only that who signed was someone eligible. That is, not reveal the actual public key used to sign, but just that the public key is included in some list of eligible public keys. And then we have the link between signatures created by the same voter so that we can prevent double voting. Otherwise, it will be very easy to hide inside the group and vote multiple times. Linkable group signature do exactly this. They reveal only that the public key belongs to a group, and the actual key stays hidden. And moreover, we have one of the elements of the signature that will collide if the multiple signatures are performed even on different messages. So it will be easy to detect if someone tries to vote multiple times. We still have a lot of problems. That is, a classic linkable group signature scheme has the size proportional to the number of public keys in the group. This means that it is utterly impossible to use the group coincident to the whole list of eligible voters, because otherwise we would have huge signatures that will be completely unusable. But if we allow users to choose their own subset, there are problems with coercion resistance. And this is a hard problem to solve. And moreover, the coercer can still ask for another signature, even if the vote is not cast, but just ask for a signature to track whether another signature of that will be linked with this appears on the bulletin board, on the list of votes. To solve this problem, there are some advanced cryptographic scheme that basically have the linking can be done only with some private key that is managed by an authority, so no one other than the authority can actually check whether someone voted multiple times, and this prevents some attacks. And for the practical aspects, there are some ways to basically fix the set of keys and just issue some access keys, let's call them that, only to eligible voters. But they are quite complicated, so I will not go into them. To go to the end, to have some coercion resistance, the basic idea for coercion resistance is to let voters fool the coercers by pretending to comply and actually do something else. So we need some sort of information can be spoofed, but remains indistinguishable from the real one. So we want someone that the user can easily forge, but still not reveal that is forged. The problem is with verifiability, that the voters should be convinced that they received some info that is genuine, even if it's indistinguishable from a forged one, and still be able to fool the coercer. So only the voter should be able to verify this statement. And in cryptography, we have a very nice thing called designated verifier zero-knowledge proof that does exactly this. Basically, the idea is very simple. Just have a disjunction between the info is real and the prover knows the private key. That is, one of these statements is true, but we will not know which one. The voter controls the key pair, does know the private key, and this means that the authority that computes originally the proof does not know the private key. So the voter knows that this proof will prove that the information is real because it knows that the prover does not know the private key. But the coercer can still be fooled because if the coercer asks something from the voter indeed knows the private key. So the coercer cannot be convinced by any proof that is given by the voter. The problems, of course, is that how can we make sure that the voter knows the private key? Because if the coercer manages to get the prover to use a public key whose private key is not known by the voter, then also the coercer is convinced by their proof. And of course, the very interesting problem, what is this info and how it can be used? The basic idea is that this info is the authorization code that I mentioned earlier to authenticate the votes, so that I can produce a vote that will be not counted as a real one because it will be not verified as a real group signature, but the coercer cannot verify that I actually used a fake or a real credential. This is basic idea. I had also something on Benero challenges. I see that I'm running a little late, so I will go very quickly on this. The idea is that we do not trust even the encrypting device, so we want to challenge the encrypted device to behave honestly. That is, we ask to reveal the randomness used to encrypt, and if we catch, if the device has behaved honestly, we will be able to check with another device that the encryption is indeed correct and the actual vote was encrypted. Of course, we want to preserve privacy, so we should not spoil, we should not cast the ballot that we open this way, because otherwise the other device knows what how we voted. So we should perform this challenge in this way. We repeat multiple times to have more probability to catch a cheating device. And first of all, we decide whether to vote or spoil the ballot. If we decide to spoil the ballot, then we choose a random preference, ask the device to encrypt this random preference, and afterwards we ask the device to reveal the randomness and we check. When we decide to cast, after one or more checks, then we do not ask to reveal the randomness and simply cast the vote. What's the problem with this process? There is pure usability. It's quite a difficult process to understand, especially for a layperson, and also more difficult to perform correctly because you have to choose randomly whether to spoil or not, which preference to use, and so on. And the other problem is that the actual cast ballots are not audited. There are some ideas, very cutting edge, that are used to go around these problems, but this is still a very open research problem, how to effectively check the trustworthiness of the encrypting device. So to conclude, we have that coercion resistance is very hard. And in general, we have to rely on some quite strong assumptions. For example, untappable channels for the delivery of some information, or safe environments where to perform some operations. We have seen that often verifiability clashes with privacy and coercion resistance. Then we have usability that has to be taken in consideration, and this is quite hard. And beside all that, the implementation is not straightforward. There are a lot of complicated things going around, so a lot of things that can go wrong. And last but not least, we have that the public has to trust the system. Otherwise, all the system is worthless. And this is a very open problem and a hard one. So I thank you all for your attendance. If you have any question, I will be here.